Hello, today we'll continue the discussion on finding the optimal hyperplane using the dual Lagrangian. We have seen that to find the plane with the maximum margin, the objective function obtained is this and under the linear constraints. However, we mentioned that we would continue further to solve it using convert it into a equivalent formulation using the Lagrange multipliers, and we had obtained this dual Lagrangian objective function. We slightly investigate further. For the recap, we write the the Lagrangian using our optimization objective function of half mod w squared and alpha I, which are the Lagrange multipliers, one each for our constraints. And we see that L should be minimized with respect to WB and maximized with respect to alpha I. Now, we take the partial derivative of L with respect to WB. Doing this, we take del L by del W, which is this, and it gives us W is equal to the summation over all samples alpha I, yi, xi, and differentiating taking the partial derivative with respect to B gives us this quantity summation of all alpha I, yi is equal to 0. When we plug these values of W and this equality into the function which we had obtained in the previous slide, we get the dual representation of the problem, the SVM optimization problem. Now, when we look at this under the constraints, of course, alpha I are all positive, 0 or greater than 0, and as mentioned, summation alpha I yi equal to 0. Now, so this is what we have obtained. The L dual in terms of alpha I, alpha j, since it is for pairs of samples, alpha I, alpha j, yi, yj, and xi dot xj. And the constraints are alpha is all positive and this sum is equal to 0. Now, we can solve this L dual using any quadratic problem solver and get the values of alpha I. So, having obtained alpha i's, now we wish to find the weight vector and the bias, the W and B, which will define our decision boundary. Now, according to the KKT conditions, we have this product alpha I multiplied by this value is equal to 0. So, this gives rise to two cases since there are two components in this product. So, alpha I equal to 0, so that the product is 0, or the other component which is yi multiplied by wx plus b minus 1 equal to 0, or equivalently y into this equal to 1. So, two cases, either alpha is 0 or the other component equal to 1. Now, if alpha I is greater than 0, this means the other component is 0. For the product to be 0, we were talking about this product, right? Yi into wxi plus b minus 1. So, if this product has to be 0 and this is non-zero, implies that the second component is 0, or equivalently yi into this equal to 1. This we have seen that holds true when the point xi is a support vector. This is a very important observation. And on the other hand, when this value is greater than 1, this product is greater than 1, then alpha I equal to 0. And when is this product greater than 1? for all those values, see we had this decision boundary. So for the samples which lie away from the decision boundary, for those values, the product is greater than 1. So this implies xi is not a support vector. So knowing the alpha i's, we compute W by summing over only those xi's where alpha is greater than 0. That means where xi is a support vector. Okay, so we get the W, and this B is obtained by the average value of all these BI's for each of such alpha I which is non-zero or which belongs to the support vector. So we have now obtained the W and B, right? So now what is the SVM classifier which we get having calculated, computed W and B? So given the optimal hyperplane defined by this WB for a new sample U, you can predict it as y hat. The class of this is the sign of WTU plus B, where this function returns a positive 1 if the argument is positive and a minus 1 if the argument is negative. So now we have reached a point where we can compute WB for the optimal hyperplane using the dual Lagrangian optimization function, which helps us to find the alpha i's, and we conclude that these alpha i's are non-zero for the support vectors. So these are used to find the W and B, which gives us the SVM classifier. So we stop at this today. Thank you. Thanks for watching.